My name is Dimitri Yatsenko. I'm Chief Science and Technology Officer at DataJoint. So this talk will be a little bit different. We'll talk about a whole range of projects and focus about actually how to organize and orchestrate projects that involve a lot of computing, more complex multimodal data, modalities combined, and how to use technology to enable all of it. And we'll talk about focus on Neuropixels, but also talk a lot about how to build more experiments. So this is a brief. There's so much to talk about here. I'll have to be selective, and I'd rather show a lot more than talk. So I'll switch between tabs and show a couple of things. So I may not be able to cover everything. I kind of watch by your reaction what's boring and what's more exciting, and focus on that. So some of this, I want to talk about how we use the DataJoint platform to orchestrate some of these studies. Some of the studies we already talked about, mentioned here. I'll focus on them, and on the ones that are most familiar have already been mentioned here. And really, I'll try to focus on this first point, on this concept of computational databases that can be used to capture in a reproducible way big chunks of the scientific process of the data operations. And go over some prominent projects. So DataJoint Elements is a U24 project that we're completing now. We're in the last, it was a 5-year project, and I'll report some of the results. And we're focusing on data publishing, and this is something we haven't talked about a lot today, specifically Dandy and Ember, but also with other platforms as well. And if we have time, and if we're excited, we can talk about how to implement different levels of AI assistance on the level of code assistance, more co-scientist layer, and even a higher level of abstraction, more strategy. So a little bit about DataJoint. So DataJoint began as a stealth skunkworks project at Baylor College of Medicine. While I was a grad student, I started developing it around 2009 and made it an open source project in 2011. And that's when we started working. After I graduated, we immediately started working on this big project, Microns. And I stayed in the same lab for my postdoc, and at the same time launched the company DataJoint to help labs. This was with a DoD grant to help many more labs scale their operations. This was also when a lot of collaborative projects started, like a lot of U19s and the International Brain Lab, a lot like Moser Lab, a lot of big labs that needed big operations. And we also got this U24 grant to use DataJoint to build standard pipelines for neurophysiology, and I'll talk about those a bit. And then about 3 years ago, we got another SBIR grant to build a commercial platform now, not just services, but also platform, and we'll talk a little bit about that. And a lot of our current focus on how to use AI to make research operations much more efficient. So the fundamental problem we're solving is to streamline scientific data operations, make them much more trustworthy, shareable, reproducible, and enable AI integration. And so fundamentally what we do is we operate experimental data pipelines. So to combine data, code, dependencies, environment. So fundamentally, every project has to solve the same couple of problems: how to manage code and data in a way that can be shared easily, that can be reproducible, and that after the student leaves, 10 years down the road, you can still get back to it, and it's still all there and working. And so we start with this open source core where DataJoint implements this concept of computational databases. It really relies on just a couple of elements: code repository, GitHub repository, or Git repository, a relational database that manages all the metadata and the structure and the dependencies, and an object store, which can be a file system for managing big data. And so this type of core that's now actually, this is new, is developed to a spec. There is a new spec document, DataJoint specs, This is for version 2.0. I'll talk about the big major release that's coming upcoming. So all of this is developed in open source and this core. And this allows labs to interchange their pipelines. So about 100 neuroscience labs use it to run their pipelines. I'll mention a couple of big projects down the road. But what labs have to make it all work easily or on scale, labs have to build a lot of infrastructure around that. Things like integrating instruments. So for example, integrating with Bonsai, integrating with OpenEFIS to ingest all the data, all the visualizations, the publishing interfaces, job orchestrations, staging space, that's where the data before it's structured is positioned, and then electronic lab notebooks. So these types of things are not standardized across different labs, and they don't have to be. And we build our, but because the core is standardized, they can still exchange the whole pipeline, but what they build around it can vary by a lot. So we focus on this center part, and then our commercial platform that I'll show implements all the remaining, that remaining ecosystem. And then finally, what is really changing the world right now is somehow AI is proving extremely surprisingly adept at helping with code, and it doesn't replace humans, but it helps us become much more proficient. So, so in labs that implement this process, this is basically you build a data analysis pipeline that manages all the data. It becomes your system of record that's shared. Your PI can see, or if you're the PI, you can see what everybody's doing in the lab. That becomes that pipeline, and all the applications and instruments talk to right into that pipeline. So I'll explain the fundamental concepts, but here's the main idea. To build such pipelines, we rely on solid computational principles, we build, it's very data-centric. There are lots of workflow systems that are more computational workflow-centric. Here's data-centered. It's very similar to how spreadsheets work. So spreadsheets really changed business when Apple II came out with VisiCalc. That was the killer app. Everybody was amazed that you can build formulas, like a spreadsheet with some cells that have values and some cells that have formulas. And then you can just automatically update everything. This is a very similar concept, but on the scale of large data. So we built a database where some tables represent data, a task, manual task, like acquiring the data or entering the data. And some steps are automated that are associated with Python code that performs computations, and they're performed automatically. And I'll demonstrate how that works. And then labs build these massive data analysis pipelines that reflect the complexity of, so this is from a 2015 preprint. This was a while ago. A lot of labs have been building these types of computational pipelines, starting with the green nodes that represent acquired data that comes from the external world, and then these red tables that perform computations. So I'll do a quick demo just to demonstrate, and then show a whole bunch of projects. I'll show EFIS a little bit later, but I'll show a very, very simple demo where we built a simple pipeline from scratch. So right now it's empty, and we'll just go ahead and build one. So I'll go to a notebook, and let me clear this. And I've used this before, if you've seen this before, but this is one of the simplest. It's not a scientific experiment. We just use Julia sets. It's a mathematical, like Mandelbrot set, mathematical concept, but we'll just to quickly illustrate, like a quick 5-minute demonstration. So first, let me make it bigger so everyone can see. So first, the concept of Julia set. A Julia set is a very simple formula. It's a recursive algorithm with just one simple, very simple formula right here in a complex plane. And if you run it with different seeds, did I not restart the kernel? Okay. You get these beautiful images. It's just one of the most surprising. They were discovered at the beginning of the 20th century, and it was just very, very surprising. But I'm just using it here to illustrate a point. One cool thing about them is that you can zoom in infinitely, And depending on the starting seed and where you focus, you'll get very infinite diversity of these beautiful patterns. So for example, here is a collection of 6 seeds. And if I calculate 6 patterns, you get this beautiful, looks like astronomy or some subatomic particles or something. So let's build a DataJoint pipeline that uses these. And so we just do some imports primarily to demonstrate image filtration. And I open here at this step, I create a schema. This is just, we start our pipeline. And I start building these tables. The first table, and it's declared as a class in Python, defines the parameters of it's a Julia specification. So it has the seed, real and imaginary component, size, center, zoom, and because this is scientific data is noisy, so we have a noise level. So these will be noisy images. So this is the first node in our pipeline. And I can insert some data into it. So I'll just insert one row into that table. I can go back to now our navigator, refresh. And so here's our first node in our pipeline. I can switch between the data and the structure. So here's our first row in this table. So I'll go back to the pipeline. I'll skip this. This is inserting 6 more. I'll do that later. So now I define my first computational node. And what in its definition, it points to the Julia spec. And then it defines 2 things to compute, an image and then a compressed image, which is an attachment of a PNG file. And then computed nodes have this make methods. This is your formula. This is how you do the computations. All make methods have the same structure. They fetch the data from upstream in the pipeline. Then they perform some computation. In this case, it calls the Julia function to compute Julia image, add some noise, create a PNG, and then at the end, you just insert it into some. So when people work with DataJoint pipelines, they typically don't think about file formats. They insert arrays, get back arrays, and all the conversions in the file saving is done by that. So we just define this node. And then typically when you set everything up, you can automate it. So as soon as new data appears in the pipeline, this computation starts kind of like in your Excel. When you update values in all the formulas that use them, update them. Here, we are still managing this explicitly. We call the populate function. The populate function does exactly that. It looks what's not yet computed and calls this computation. And so it just filled out that one row in the table. If I run this again, then nothing is done because that computation is already performed. This is our very, very first simple pipeline. So if I refresh here, this is what the pipeline looks like. The top node with the specification, the bottom node that performed the computation. And then I go back and let me define a couple more nodes. And let's define a few images that we will, or if you, so I'm just retrieving an image just to show what it looks like. Now it's the same image just with noise. And I'll declare one more table. This is a lookup table, which means that it's part of the schema definition, really not part of the table, part of the data. It defines different filtering methods like Gaussian, median, wavelet, total variation. And then the final table is Julia denoised. It has 2 pointers. One is to Julia image and one is Julia denoise method. So it can compute any combination. So if we have 7 Julia images and 4 denoising methods, it will perform 28 computations. So let's define that. So the make method again does the same thing. It retrieves the data from upstream. It performs the computation here with a big switch statement. I assume most people here are somewhat familiar with coding. And then also save the image. And then at the end, you just insert. So I define this table, and we're done. So now our pipeline is defined. If I go back to the pipeline, this is our entire pipeline. So we have a Julia specification that computes a Julia image. Then we have denoise methods, and then we compute the denoised result. So this is the simplest pipeline I could conceive of that actually demonstrate. So let's perform the final computations, and I'll show you the main. Did I switch? I switched to the back to the notebook. And so let's insert 6 more Julia specs. So now if I run Julia image populate, it will compute the remaining ones. And if I compute the very last one, it performs all of the 28 denoising computations. So what labs do, they use this type of approach to define their computations behind their spike sorting, calcium imaging, and now I'll talk about some projects. So this is how data scientists interact with the pipeline, how scientists that run the experiment interact with the pipeline. They interact through a dashboard. A dashboard allows you to interact with your pipeline during your experiment. This is where you enter data. So, and these are highly customizable, and show you one for spike sorting, for calcium imaging, and then in the plot. So you want to review your Julia images that we just computed. You can select the result and see your results. So this is done by integrating Plotly Dash. And again, many labs, some that use DataJoint. This part is not how you implement this. This is not standardized. How the pipeline is defined is standardized. But many different teams over the years have implemented various ways of put all the visualizations around it. All right, and then here's the denoised images. So you can review the results of various denoise. One problem with fractal images, they don't have any characteristic scale or frequency. They're very difficult to filter because there's nothing, you can't tell noise from detail. So it's probably not a good scientific explanation. So let me show you some of the pipelines for typical experiments, actual experiments, and some of them have been mentioned here. For example, Project Eon, Gonzalo talked about it, a couple of other people talked about it. It's this is what a typical pipeline. This does not include electrophysiology, but includes other like streams of information from Bonsai. And so each of these schemas, as you open all of the steps, this project now is year 5, so they'll be collecting a ton of data. It's continuously running and this is a copy of their schema, not the actual schema. The actual schema runs within their institution. So what you're seeing is running in the cloud, but the whole application, everything can be set up to run completely within the lab. This is one big change over the last couple of years. And so I'll show specific pipelines for spike sorting as well. But let me talk about a few projects. So how typically labs operate. So we primarily focus on building the tools and the operations, and then it's for the labs to implement what they need for their studies. We provide a lot of standard things and implemented them. So for example, this was a couple of years ago in the lab, the Sabatini lab, and this is Janet Wallace, and we did a 3-day workshop to teach the whole lab, 50 people, how to run these types of pipelines. One big project that just got completed that where the neurophysiology part relied on DataJoint, where about 100 people contributed to the pipeline, was the Micron project. It was published. The results were published after 9 years. This is the reason I stayed in the same lab for my postdoc, because this was a massive project. We developed a lot of infrastructure for it. And so the Allen Institute was led all the structural imaging, electron microscopy, and at Baylor College of Medicine, we focus on the physiology data. There are lots of ways to access it, and we're now, so it's been exported to Dandy. And I will not get into too much details, but this is this is where we studied a cubic millimeter of the visual cortex, recorded from every cell using multiphoton imaging. About 90 minutes, each cell saw about 90 minutes of visual stimulus. And then all of this was reconstructed in electron microscopy. To my maybe a little embarrassment, but not, I mean, I'm proud of this work, but right now it's still pretty difficult to work with the data. It was published, the standard way was just an SQL dump, which is very difficult to work with. We also host an instance of the database that people can work with. So there's an example on GitHub. It's been also exported into Dandy, in NWB format, and that may be one of the easiest ways to work with it. And then also, we are directly collaborating with several, like with Neuromatch, with a couple of other universities to actually take the processing to the next step. This is Project Eon that has been mentioned here a couple of times already. So this is one of the most remarkable experiments because the trial there is social behavior, two mice approaching each other, and the recordings are continuous. It's very large scale. So very proud of this work, and it's in year 5. We've been at work, like one example, this was really cool because we started with Marshall Schuler at Johns Hopkins in June of 2024, implemented with them the pipeline that involved deep lab cut and spike sorting. Within 60 days, the whole pipeline was producing massive data, and they're able to just collecting about a terabyte per day. Since then, it's automated, so the researchers really focus on their work. Sequencing information, I'll kind of glide through it. So one of the upcoming big projects, one of the biggest projects right now in neuroscience is that's just kicked off. It's kicking off now. It's called Project Scene, funded by the Simons Foundation. The great thing about it is it's a 10-year project, so really big things can be done. So this is where a lot of DataJoint pipelines will be developed for behavior analysis across species, more like foundation models across different species. I guess they don't want to use the word foundation models for this, but it's across rodents, primates, bats, and it involves 20 principal investigators. If you go to the website on the Simons Foundation, you can see which labs. A lot of their names have been mentioned here today already. So I'll review briefly DataJoint elements. So this was, once we started building these pipelines on scale, still every lab was doing something else. So we got a grant 5 years ago to standardize. And this is where some of the, so we basically produce reference pipelines for all the kind of major modalities of neuroscience, and we develop them in of systems neuroscience, of neurophysiology, maybe not, it's still too presumptuous to say all of neuroscience, but all of the kind of bread and butter, calcium imaging, spike sorting. Spike sorting was one of the first. That's what Neuropixels really took off, started 5 years ago when a lot of labs were adopting it, and so this is where we can, and so we implement them using a common language in the sense of how the data are organized, and can quickly, so usually a typical project, multimodal project that involves 2, 3, 4, 5, 6 of these modalities in one study can be put together in 1 day. And so that's something that we've been able to do on scale. And this is what a typical pipeline looks like. It's a directed acyclic graph. You start from the top and follow through it and build interfaces around it. So this is more from a data scientist point of view. So the green nodes, if you zoom in, you may probably not see, but it's not that essential here. You'll see a lot of these. You start with a subject typically, or some lab information, but usually it's subject your mouse, then sessions, then recordings, scans, and then different branches go into all the modalities, and these are modular software pieces that then come together for analysis. And all of this is documented under docs.datajoint.com.elements. And so if you go, for example, into, and they all come with interactive tutorials. It's containerized, so it can run out of code spaces on GitHub, but it can also, and I can show you some of this, how to run it inside the platform as well. So this containerization allows to quickly move between running it on your platform, running on GitHub, running in AWS. So the idea is to make it independent of the infrastructure that you're committed yourself to. And we can look, for example, into electrophysiology, and this very much focuses on Neuropixels because that has been for the past few years the fastest growing modality, and so this has a complete documentation. But also, if you don't know this feature, it's really cool. When you go into code, now you have the cloning functions, but you also have code spaces functions. Code spaces means that you can launch the tutorial, launch the whole infrastructure right here. You cannot do spike sorting unless they change something. You can have a GPU instance. So maybe they allow you now. Does anybody know if GitHub gives you GPU instances now? But I think they do. You have to pay extra, but you can run you can clone run on your laptop, but you can walk through the same. We have a pre-sorted data set here. You can walk through the whole process and see the results. So if you go into, once you launch the notebook or the code space, you can go into tutorial. Hey, Marika, is that you? Okay, so Marika, your phone is your microphone is on, so in this tutorial, it walks you through a process of starting a session. It shows the pipeline.
The big presentation that I was getting ready for this past week. I think the demo.
I have to do it.
Okay, got it. And so, and walk you through, it walks you through this process of how to populate, how to run the analysis, and how to synchronize it with other modalities. All right, in the remaining time, I'll talk a little bit about the whole ecosystem. So all of these pipelines rely on a lot of open source tools. This is just a small selection. There was a paper published by Odin. It's a preprint. Odin is the Open Data Neuroscience, run by Nima Degani and by, well, actually now by a whole community. But they published this overview as of 2023, and then they updated it just last month. And basically, all the tools fit together. All the tools work on their data, but to put them all together into a common data analysis pipeline, you need more of a data management framework. They listed DataJoint there and Spyglass. Spyglass is developed by Lauren Frank at UCSF, but Spyglass uses DataJoint underneath. It's basically developed on top of DataJoint to combine neurodata without borders. I'll cover a couple of other things. One of the big developments is that a lot of the software that you guys develop can be used for commercial applications in industry, and a lot of pharma companies are interested to use these tools. There is a way to, we've started to work like this with Harvard, for example, around MOSIC, where we can develop a collaborative agreement with revenue sharing. As labs now need to think about how to diversify their funding, this becomes one of the streams. Quality control, again, as I described, I have a lot more things to talk about than we have time, so I'll zoom through this and answer your questions. So one big thing, the final thing I'll describe as part of finishing the U24, we're preparing DataJoint 2.0 release. This is the biggest, somewhat backward incompatible in terms of some of the code change that really focuses on being able to publish data and share data between projects. So there is a spec describing it, and we're changing the license to Apache from LGPL to make it more friendly to include in most other projects. It changes the export format, and this is where we're meeting with Dandy and Amber. These are two major data archive initiatives funded by the BRAIN Initiative. Dandy has been around for a while, and Ember just started a year ago, but they fundamentally are the same platform. They use the same architecture. Ember is focusing on behavior and Dandy on neurophysiology. We didn't get to AI, but we can talk about it after the meeting. All right, thanks so much.